History of Uranus, the coldest and strangest planet in the solar system. We continue our journey through the solar system. After exploring Saturn's hexagonal storms and its hidden oceans, it's time to venture even farther out, toward the icy regions, to encounter one of the most enigmatic and bizarre worlds, Uranus, the ice giant that defies every planetary convention. This planet isn't just a world of extreme climates and exotic compositions, but represents a true cosmic anomaly that continues to surprise astronomers. A giant that rotates completely on its side, like a ball rolling along its orbit, alternately showing its poles to the sun for entire decades. A world where seasons last more than 20 Earth years, and where the atmosphere reaches temperatures so extreme that it becomes the coldest place in the solar system, even more frigid than Neptune, despite being much closer to the sun. What do you say? Shall we pay it a little visit? Uranus is a planet that defies every expectation. The seventh world from the sun, so distant that sunlight takes almost 3 hours to reach it. So cold that methane crystallizes in its upper atmosphere. So strange in its rotation that astronomers have had to redefine the concepts of North Pole and South Pole to describe it. With its characteristic blue-green coloration and its incredible axial tilt of 82 degrees, Uranus literally appears lying on its side as it orbits the sun, creating a seasonal system unique in the solar system. But what makes this icy giant so special? With a diameter of 31,763 miles or 51,118 kilometers, about 4 times that of Earth, Uranus is the third largest planet in the solar system, but fourth by mass, since its density of 1.27 grams per cubic centimeter or 79.3 pounds per cubic foot is significantly lower than that of Neptune, 1.64 grams per cubic centimeter or 102.4 pounds per square foot. It orbits at an average distance of 1.78 billion miles or 2.87 billion kilometers or 19.2 astronomical units from the Sun, completing one revolution in 84 Earth years. Essentially the duration of an entire human lifetime. The ice giant rotates on its axis in 17 hours and 14 minutes. But here begins its strangeness. The rotation axis is tilted 82.2 degrees relative to the orbital plane, which means Uranus rotates practically on its side. This unique characteristic means that during the long Uranian year, each pole receives continuous sunlight for 42 Earth years, followed by 42 years of complete darkness. Surface gravity is slightly less than Earth's, 0.886 times. So a person weighing 154 pounds on Earth would weigh about 136 pounds on Uranus. The average temperature in the upper atmosphere is minus 371 degrees Fahrenheit or minus 224 degrees Celsius, making it paradoxically colder than Neptune, despite being closer to the Sun. This thermal enigma is due to the fact that Uranus emits much less internal heat compared to other gas giants, for reasons still not completely understood by planetary science. A new planet after millennia. The story of Uranus's discovery is as fascinating as the planet itself. Until March 13, 1781, humanity knew only 6 planets in the solar system, from Mercury to Saturn. That night, in the spa town of Bath, England, a German musician, naturalized as British, named William Herschel was conducting a methodical observation of the sky with a reflecting telescope of his own construction, equipped with a 6-inch or 15-centimeter diameter mirror. Herschel wasn't a professional astronomer, but an enthusiast who had developed extraordinary skill in telescope construction. Together with his sister Caroline, who would become the first paid woman astronomer in history, William spent nights observing double stars in an attempt to measure stellar parallaxes. That particular evening, while scanning the constellation Gemini, he noticed an unusual object that appeared slightly larger than surrounding stars and showed a clearly visible disk. Initially, Herschel thought he had discovered a comet. The object moved slowly against the stellar background, a characteristic that clearly distinguished it from fixed stars. But in the following weeks, when other astronomers calculated its orbit, it became evident that this was something much more significant, a new planet, the first to be discovered in modern times, and the first identified thanks to a telescope. Herschel's discovery not only doubled the known size of the solar system, but also demonstrated that worlds existed beyond the imagination of the ancients. As a reward for his discovery, King George III appointed Herschel court astronomer and granted him a pension that allowed him to dedicate himself completely to astronomy. Herschel initially proposed calling the new planet Georgium Sidus, or George's star, in honor of the sovereign, but eventually the name Uranus prevailed, suggested by German astronomer Johann Bode, maintaining the tradition of naming planets after figures from classical mythology. Composition and structure: a different giant. Uranus belongs to the category of ice giants, a distinction that separates it both from gas giants like Jupiter and Saturn and from the inner rocky planets. Its composition is dominated by materials that astronomers call ices, not in the sense of frozen water, but volatile substances like water, methane, and ammonia in supercritical phase, along with hydrogen and helium. Uranus's internal structure is organized into three main layers. At the center lies a small rocky core composed of silicates and iron-nickel, with a mass of about 0.55 Earth masses and a radius representing less than 20% of the planetary radius. This core is surrounded by a massive mantle of hot ices, mainly water, methane, and ammonia in fluid form, which constitutes most of the planet's mass, about 13.4 Earth masses. Everything is wrapped in a relatively thin atmosphere of hydrogen and helium that represents only about 0.5 Earth masses. What makes Uranus truly unique is its magnetic strangeness. The planet's magnetic field isn't aligned with the rotation axis as would be expected, but is tilted a full 58.6 degrees relative to it. Moreover, the center of the magnetic field is offset by about 1/3 of the planetary radius from the planet's geometric center. This bizarre configuration suggests that the magnetic field might be generated not in the deep core, but in the intermediate layers of the conductive ice mantle. Uranus's atmosphere is composed of 83% molecular hydrogen, 15% helium, and 2% methane, with traces of water vapor and ammonia. It's precisely the methane that gives the planet its characteristic blue-green coloration. This gas strongly absorbs red light while reflecting blue and green wavelengths. The presence of methane in the upper atmosphere was unexpected, given that at those temperatures, minus 371 degrees Fahrenheit or minus 224 degrees Celsius, it should be completely frozen. An extreme and mysterious climate. Uranus's climate is governed by its extraordinary axial tilt, which creates a seasonal system unique in the solar system. Unlike other planets where seasons are caused by varying distance from the Sun, on Uranus they depend entirely on which pole is facing our star. During Uranian summer, one pole receives direct and continuous sunlight for 42 Earth years, while the other remains in complete darkness. Then, the situation reverses for another 42 years. Despite this extreme configuration, Uranus shows surprisingly fast winds that can reach 560 miles per hour, or 900 kilometers per hour, among the fastest in the solar system. These winds blow mainly in the direction of the planet's rotation, but the mechanism that powers them remains mysterious, given that Uranus receives so little solar energy and generates very little internal heat. The Voyager 2 probe, which visited Uranus in 1986, observed an apparently calm atmosphere with very few visible features. However, more recent observations from the Hubble telescope have revealed that Uranus can develop dynamic storm systems, especially when approaching equinoxes, moments when both hemispheres receive solar illumination. A particular mystery concerns Uranus's atmospheric temperature. Despite being closer to the Sun than Neptune, Uranus is systematically colder. While Neptune emits 2.6 times more energy than it receives from the Sun, Uranus emits almost the same amount it receives, suggesting a much less thermally active interior. Theories range from different internal composition to consequences of the impact that might have caused its anomalous rotation. Hey guys, just a moment before we continue. Be sure to join the Insane Curiosity channel. Click on the bell. You'll help us to make products of even higher quality. A complex system of rings and moons. Uranus possesses a ring system discovered only in 1977, when astronomers aboard the Kuiper Airborne Observatory observed the planet occulting a distant star. To their surprise, the stellar light dimmed several times before and after the main occultation, revealing the presence of thin, dark rings. Uranus's ring system is composed of 13 confirmed rings, very different from Saturn's spectacular ones. Uranus's rings are extremely dark, reflecting only 2% of incident light, and are probably composed of organic material altered by radiation. The most prominent is the Epsilon ring, about 62 miles or 100 kilometers wide, with particles ranging from fine dust to boulders several yards across. Uranus's 28 known moons are equally unique in the solar system. Unlike moons of other planets, which take names from Greek or Roman mythology, those of Uranus are named after characters from the works of William Shakespeare and Alexander Pope, earning them the nickname literary moons. This tradition began with John Herschel, son of Uranus's discoverer, who in 1852 named the first 4 known moons. Besides the 5 major moons, Uranus possesses 23 minor moons discovered mainly by the Hubble telescope and advanced ground-based observations. 10 of these were identified by Voyager 2 in 1986. Cordelia, 25 miles or 40 kilometers in diameter, Ophelia, 27 miles or 43 kilometers, Bianca, 32 miles, 51 kilometers, Chrysidia, 50 miles or 80 kilometers, Desdemona, 40 miles or 64 kilometers, Juliet, 58 miles, 94 kilometers, Portia, 84 miles or 135 kilometers, Rosalind, 45 miles or 72 kilometers, Belinda, 56 miles or 90 kilometers, and Puck, 101 miles or 162 kilometers. These small moons orbit between the rings and major moons, some acting as shepherds to maintain ring structure. The outer irregular moons discovered between 1997 and 2003 include Caliban, Sycorax, Prospero, Setebos, Stefano, Trinculo, Francisco, Margaret, and Ferdinand. These moons, with diameters between 5 and 93 miles or 8 and 150 kilometers, orbit at enormous distances, 2.5 to 12.4 million miles or 4 to 20 million kilometers, on retrograde and highly eccentric trajectories, suggesting they are asteroids captured by Uranus's gravity. The most recent discovery dates to November 2023, bringing the total to 28 confirmed moons. Miranda, 294 miles or 472 kilometers in diameter, 80,654 miles or 129,800 kilometers from Uranus, the smallest of the major moons, is perhaps the most fascinating and mysterious. Its surface presents a patchwork appearance with terrains of different ages juxtaposed in apparent random ways, a unique characteristic in the solar system. Canyons 12 miles or 20 kilometers deep, 12 times deeper than the Grand Canyon, carve through its icy surface, while oval structures called coronae indicate complex geological processes. Its density of 1.2 grams per cubic centimeter or 74.9 pounds per cubic foot suggests an ice-rich composition. Some theories propose that Miranda was fragmented by catastrophic impacts and then reassembled under its own gravity, explaining its fragmentary appearance. Ariel, 719 miles or 1,158 kilometers in diameter, 118,000 miles or 191,200 kilometers from Uranus, is the brightest of the Uranian moons, with an albedo of 23%. Its relatively young surface shows few large craters, but many small ones, indicating recent geological renewal events. Intersecting valleys and scarps across the surface, some partially filled with material that may have upwelled from the interior. Its density of 1.67 grams per cubic centimeter or 104.2 pounds per cubic foot indicates a mixed composition of ice and rock in nearly equal proportions. Umbriel, 726 miles or 1,169 kilometers in diameter, 165,300 miles or 266,000 kilometers from Uranus, is the darkest of the major moons, reflecting only 16% of incident light, blacker than asphalt. Its ancient surface is densely cratered, similar to lunar highlands. A mysterious bright ring, 87 miles or 140 kilometers in diameter, stands out on its dark surface, whose origin remains unexplained. Its density of 1.4 grams per cubic centimeter or 87.4 pounds per cubic foot suggests a balanced composition of ice and rock. Titania, 981 miles or 1,578 kilometers in diameter, 271,100 miles or 436,300 kilometers from Uranus, the largest moon in the system, presents varied terrain with craters, canyons, and smooth plains. Valleys up to 62 miles or 100 kilometers deep carve the surface, testifying to past tectonic activity. Its density of 1.71 grams per cubic centimeter or 106.8 pounds per cubic foot is the highest among Uranian moons, indicating greater rocky content. Recent models suggest Titania might harbor a residual ocean up to 31 miles or 50 kilometers deep beneath its icy crust. Oberon, 946 miles or 1,523 kilometers in diameter, 362,600 miles or 583,500 kilometers from Uranus, the outermost of the major moons, shows an ancient, densely cratered surface, reminiscent of Saturn's moon Rhea. Several craters display bright rays and central material, indicating relatively recent impacts. Its density of 1.63 grams per cubic centimeter or 101.8 pounds per cubic foot is similar to Titania's. Like Titania, it might hide a subsurface ocean maintained by thermal metamorphism processes. Visited by a single probe, Voyager 2. Uranus's close-up exploration has been entrusted exclusively to the Voyager 2 probe, which reached the planet on January 24, 1986, after an 8.5-year journey. This encounter represents one of the triumphs of space engineering. Voyager 2 had to be reprogrammed to adapt to Uranus's anomalous rotation and unusual magnetic fields. During the close flyby, passing just 50,600 miles or 81,500 kilometers from the cloud tops, Voyager 2 transmitted over 7,000 images and an enormous amount of scientific data. The probe discovered 10 new moons, 2 new rings, and provided the first detailed measurements of Uranus's magnetic field. The images revealed an apparently monotonous world with an atmosphere almost devoid of distinctive features, a stark contrast to Jupiter's turbulent storms and Saturn's colored bands. However, Voyager 2's data has continued to reveal secrets for decades. In 2020, a reanalysis of magnetic data identified a gigantic magnetic bubble plasmoid that had detached from Uranus during the probe's passage, suggesting much more dynamic magnetospheric processes than initially understood. Voyager 2's scientific legacy has also highlighted how little we still know about Uranus. The probe observed the planet during southern solstice, when one pole was facing almost directly toward the Sun. This means we've never closely observed Uranus's atmosphere during other seasons, leaving many questions about its seasonal atmospheric dynamics. After Galileo at Jupiter, Cassini at Saturn, and Juno continuing to study Jupiter, ice giants remain the last class of solar system planets without a dedicated orbiting explorer. International efforts to realize such a mission are intense and coordinated. The European Space Agency has included ice giant exploration in its Strategic Voyage 2050 program, while NASA has identified a Uranus mission as an absolute priority for the next decade. Advanced mission concepts include combinations of orbiters, atmospheric probes, and even landers on icy moons. Unsolved mysteries and future prospects. Uranus remains one of the least understood planets in the solar system, with more questions than answers. The origin of its anomalous rotation is still debated. A gigantic impact during planetary formation, chaotic orbital migration, or perhaps a combination of catastrophic events. New theories suggest that instead of a single massive impact, a series of smaller collisions with moon-sized objects might have gradually tipped the planet over. Its eccentric magnetic field suggests internal processes fundamentally different from those of other giants. The lack of internal heat. Uranus emits only 1.06 times the energy it receives from the Sun, much less than other gas giants, challenges planetary evolution models. This energy deficit might be considered to the great impact that caused its anomalous rotation, possibly dispersing the planet's primordial heat into space. Even its apparently calm atmosphere might hide complex dynamics that we only partially observe from Earth. Recent observations from the James Webb Telescope have revealed unprecedented details of rings and seasonal storms, suggesting Uranus is much more active than Voyager 2 observed during its brief encounter. The most recent studies suggest that Uranus's major moons might harbor residual oceans beneath their icy surfaces. Titania and Oberon might maintain liquid layers up to 31 miles or 50 kilometers thick, thanks to late thermal metamorphism, while Ariel and Umbriel might have thinner oceans, less than 19 miles or 30 kilometers. These oceans, if they exist, might be hypersaline and therefore detectable through induced magnetic fields, opening new possibilities for astrobiology. Uranus as archetype of extrasolar worlds. Uranus and Neptune represent much more than simple curiosities in our solar system. They are archetypes of the most common class of planets in the universe. Observations from the Kuiper Space Telescope have revealed that planets with masses and sizes intermediate between Earth and Neptune, the so-called super-Earths and mini-Neptunes, are the most abundant among known exoplanets. These worlds, with radii between 1.8 and 4.0 Earth radii, represent a planetary category completely absent from our solar system but dominant in the galaxy. Most orbit very close to their host stars, completing an orbit in less than 100 days, creating extreme environmental conditions that might be common in the universe. Studying Uranus and Neptune therefore provides us with a natural laboratory for understanding physical processes that might be fundamental to billions of worlds throughout the Milky Way. The unique composition of ice giants, dominated by volatile compounds like water, methane, and ammonia rather than hydrogen and helium, represents a key to understanding how these intermediate worlds form. Current planetary formation models struggle to explain how Uranus and Neptune could have accreted their masses in their present position, where the protoplanetary disk was too rarefied and formation timescales too long. Three main scenarios compete to explain ice giant formation. Core accretion in their current position, unlikely given the low density of the outer disk. Formation closer to the Sun followed by outward migration, supported by the Nice model, and direct gravitational instability of the protoplanetary disk that would create massive protoplanets in relatively short times. The last scenario is particularly intriguing because it could explain rapid ice giant formation, even in short-lived protoplanetary disks, which exist for only a few million years. Regions of slightly higher density in the disk could collapse directly into protoplanets with planetary density and timescales of thousands of years, much faster than the 100,000 to 1 million years required by traditional core accretion. To conclude, Uranus reminds us that the universe is full of surprises that challenge our expectations. This giant that rotates on its side with its frigid atmosphere and magnetic mysteries represents a fundamental chapter in solar system history. Its discovery revolutionized our understanding of cosmic vastness, while its unique characteristics continue to challenge our planetary models. In this distant world where seasons last decades and winds blow at supersonic speeds through an atmosphere of frozen methane, we find a reminder of incredible planetary diversity. Uranus teaches us that even in the most remote and apparently inhospitable places in the cosmos, nature can create phenomena of complexity and beauty that surpasses our imagination. Okay, folks, that's all for Uranus. Our journey will continue with Neptune, the last of the major planets, a world of devastating winds and icy moons that will complete our tour of the most remote domains of the solar system.